Hi guys, in this video we are going to introduce the concept of a mole-to-mole conversion, which we will see is a way that allows us to use a chemical reaction equation and answer questions such as, for example, how much product we can make with a given amount of reactants present. So to illustrate this concept, let's go back and look at our favorite example of a balanced chemical reaction equation for the formation of water. So in this reaction, we have two H2 molecules coming together with one oxygen to form two molecules of H2O. And we saw in detail how to go about balancing a chemical reaction equation, and we can of course quickly determine by counting up the individual atom types on each side that this is in fact a balanced reaction. Okay, so now the technique of mole-to-mole conversion is going to allow us to use this sort of information, our balanced chemical reaction equation, to solve the following type of problem. Suppose you're given a balanced chemical reaction equation and you need to determine how many water molecules you can form if you're given only 4 molecules of hydrogen. So let's go ahead and write this out. We are given 4 molecules of hydrogen. So if you write that out, we'll have all 4 of them, 1, 2, 3, and 4, present right here. And our goal now is to figure out how many water molecules you can form using this balanced chemical reaction equation. Okay, so our first step then is going to be to really focus in on that balanced chemical reaction equation, which essentially gives us the recipe we need to follow for forming water. And specifically, what this balanced chemical reaction equation tells us is that for every 2 molecules of H2 that are present, you are going to form 2 molecules of H2O. Okay, so let's go ahead and start by taking our first 2 H2 molecules and converting them over there to waters. Right? Once we've done that, we now have formed 2 waters, but we still have 2 more H2 molecules ready, willing to react with oxygen to form an additional 2 H2Os. And so we can see here that reacting the last 2 molecules of H2 forms the 2 additional molecules of H2O, resulting in 4 water molecules. Therefore, we can conclude that the complete reaction of 4 molecules of H2 forms exactly 4 molecules of water. Okay, so hopefully, by drawing out the individual molecules and looking at that balanced chemical reaction equation and sort of carrying out the reaction one step at a time, we can understand the underlying logic behind solving these problems. But what we want to do is come up with a way for solving these problems, determining how much product we can form without having to draw out individual molecules. And obviously, if we're dealing with reactions on the order of Avogadro's number of individual molecules, we certainly don't want to be drawing them out. And so the technique of mole-to-mole conversion is what's going to actually allow us to solve this problem in a very quick and efficient manner. Okay, so we're going to look at this exact same example once again. Okay, so the first step in using a mole-to-mole conversion is to identify the given amount of starting material. In this case, we're starting off with 4 molecules of H2, and identify the product of interest. Right? In this case, it's H2O. Okay. So then you're going to use the balanced chemical reaction equation to construct a conversion factor that takes us, right, from moles of our reactant, H2 in this case, to moles of product, H2O in this case. That way, if you take your initial quantity of reactant, 4 molecules of H2, you can then directly apply this conversion factor built using the stoichiometric coefficients from a balanced chemical reaction equation to cancel out molecules of H2 and arrive at your final answer with the correct units. So notice, the units are always going to be set up so that the units of the given starting material are going to cancel out, and the desired, in this case products, is going to be the remaining unit. And the numerical value associated with that mole to mole or molecule to molecule conversion factor in this case come directly from that balanced chemical reaction equation. Okay? So we basically have constructed here a molecule to molecule ratio, right? And by constructing this ratio and doing this one step here, we've avoided the need to draw out and cancel out, count one by one individual atoms or individual molecules, which of course sets the stage for us to solve a little bit more complicated examples. So in this example, let's use our same balanced chemical reaction equation to figure out how many water molecules we can form if we're given 17.3 moles of hydrogen. So we're going to follow the same sort of procedure, figure out the reactant, product of interest. We're then going to form a mole-to-mole conversion factor, right, using those stoichiometric coefficients. We're going to be starting off with our given value of 17.3 moles of H2. We're going to make sure moles of H2 shows up in the denominator so that moles of H2 cancels. We will end up in moles of H2O. And then using those stoichiometric coefficients, we will plug in the numerical values, and we can plug through and determine that if you fully react 17.3 moles of H2, you get 17.3 moles of H2O, because we once again have that essentially one-to-one ratio in that conversion factor. Okay, so these simple examples set the stage for presenting a general method for using mole-to-mole conversion factors to determine the amount of product that can form from a given amount of reactant. Right? So the first step is to identify the starting material and the product of interest. Then you're going to use that balanced chemical reaction equation. The key word here is balanced. Right? If you do not have a balanced chemical reaction equation, then that ratio, that mole-to-mole conversion factor that allows you to convert from reactant to product, will be incorrect. So make sure it's balanced, and then you can read off those coefficients to get that mole-to-mole conversion factor. And then lastly, you can carry out the steps, and do the math. Right? So let's see a little bit more complicated example. Let's say that we are reacting hydrochloric acid with oxygen to form water and chlorine gas. And so we're given the balanced chemical reaction equation right here. Right? And what we want to determine is how many moles of Cl2 can be formed from an initial quantity of 4.3 moles of HCl. So we've identified the reactant and product of interest, right? We want to know, we're given 4.3 moles of HCl, and we want to end up in moles of Cl2. So we want to look at HCl and Cl2, like that, and use this balanced chemical reaction equation to construct a mole-to-mole conversion factor. And so based on those stoichiometric coefficients, we see that for every 4 moles of HCl that is reacted, you will get 2 moles of chlorine gas. Once you have that conversion factor, then you're ready for your final step. Simply plug in that given value, 4.3 moles of HCl in this case, multiply by that conversion factor, that ratio, and you will obtain correct units, moles HCl cancels out, and a final answer, in this case 2.2 moles of chlorine gas. So we can summarize those steps. You basically identify reactant and product. You look at those stoichiometric coefficients, form the conversion factor, use that conversion factor to carry out a change of units from our given units of HCl to our desired units of chlorine. Right. Units cancel out, and we're good to go. Okay, so in the previous examples, we've seen how we can use these mole-to-mole conversion factors to convert from a given amount of reactant to an amount of product that can possibly be formed if you fully react that reactant. Now, this mole-to-mole conversion factor concept can actually be applied to convert between any two reactant and product compounds. So let's consider a slightly different question, where in this question we're given methanol and oxygen reacting to form CO2 and water, a combustion reaction, and we want to determine how many moles of O2 are required to fully react 8.31 moles of our methanol, CH3OH. Okay? All right. So in this case, we again want to identify what we're starting with and where we want to end up. So we're going to map out that conversion. We're going to be starting off, in this case, with methanol, all right? And we want to figure out how many moles of methanol, of O2, are required to fully react with this given amount of methanol. So in this case, we're focusing entirely on the reactant side of the equation. We're given a certain amount of one reactant, and we want to figure out how much of the other reactant, O2 in this case, is going to be required. So we follow the same exact protocol that we outlined previously. We are going to focus in on each one of those reactants and construct a mole-to-mole conversion factor using those stoichiometric coefficients. In this case, for every 2 moles of methanol that reacts, it requires 3 moles of O2. Finally, we will then apply that conversion factor that we just constructed using our initial quantity of methanol, making sure that our units are set up so that moles of methanol will cancel out, multiply by 3/2 in this case, and we will arrive at our final answer. And so this really sets the stage for a more general method for using mole-to-mole conversion factors. You simply determine the reactants and or products involved, map out a conversion, use that balance. Once again, I can't stress this enough, make sure that is a balanced chemical reaction equation to construct that mole-to-mole conversion factor, and then use your unit conversion techniques to carry out that conversion, and you're home free. Now in the next video, we are going to see how we can extend this same concept one step further to deal with conversions where you are not given reactants in units of moles, but rather in units of grams. And we're going to be exploring a so-called gram-to-gram conversion.